Hi there! From the Low Power Amplifiers and Comparators team at TI, my name is Adi, and today we're going to go over common methods used to perform high-side current sensing. Specifically, we'll take a look at where one can use high-side current sensing in automotive systems and what types of circuits and devices are used in these applications. So let's start our discussion with an example from an automotive infotainment system. Here's a simple graphic that provides an overview of the various systems in the infotainment and cluster space. Many of these systems will often include an MCU or application processor for controlling various actions. The MCU is surrounded by peripheral components that perform system monitoring and diagnostic functions, such as current sensing. So really, current sensing can be found in any automotive system with an MCU, making it a very widespread function. So now that we have a feel for where you can find current sensing circuits, let's take a closer look at the circuits themselves. There are many different topologies for current sense, but in this video, we will stick to high-side sensing and focus on cost-effective solutions with comparators and amplifiers. Here you'll see two different topologies for high-side current sensing. Notice that both utilize a shunt resistor, but one method contains two components, namely a current sense amplifier and a comparator, and the other only uses one comparator. As a system designer, the first question you can ask yourself is, do I need an amplifier? A lot of times the answer is yes, and in the next slide we'll discuss this method in more detail. For many applications though, a simple comparator can work just as well, and we'll go over when to use which solution in the following slides. Let's start first by analyzing the circuit on our left. Here we see a current sense amplifier used to measure the current through the shunt resistor. We then compare the measured value to a predetermined threshold using a comparator with an integrated reference, which is shown via the red dotted lines. How do I know if I need an amplifier? To answer this question, all we need to do is think about the shunt resistor. In order to minimize power dissipation, we need to make that resistor value as small as possible. However, if we make it too small, the signal will be too tiny for either the ADC or comparator to interpret. Thus, we need an amplifier to gain up our signal. In this example, we showcase the INA240Q1 family because of their balance between accuracy and cost effectiveness. The highlighted comparator here is TLV3012Q1, a low-power AEC100 qualified comparator with an integrated reference. The integrated reference allows for easy comparisons and also saves on board space. Let's compare this common implementation to method 2 next. In this circuit, we do current sensing with just one comparator. Note that our device, TLV1701Q1, is a high voltage comparator and is powered straight from the battery, making this a true high-side sensing circuit. No separate supply is required. This standalone comparator solution is less accurate than our first method with a current sense amplifier, but it makes up for the lower accuracy with its higher speed. Additionally, this solution will result in a lower system cost because you don't have the amplifier and also because you don't need a separate power supply for the devices like we needed in method 1. However, there is always a trade-off in design, and here the use of only a comparator will require a larger shunt resistor since we don't have an amplifier to gain up the signal, and therefore a larger power dissipation. Let's compare the two solutions more closely and further examine these trade-offs. In this comparison, we weigh the various benefits of both methods. Although it seems like method 2 outweighs method 1, it's really not that simple. With method 1 and the current sense amplifier, you can read the actual value of the current flowing in your system. This is very valuable information for any application that requires accurate readings. Additionally, with method 1, you get to use a smaller shunt resistor, making it ideal for higher current applications. Method 2 is great for lower cost systems that simply need to do a quick check if the current is too high. Method 2 is easy to design and is fast acting, making it ideal for any application that does not require a precision reading of the current. It is also preferable in lower current systems that can afford the larger shunt resistor power loss. The scale can tip either way depending on your system needs, but the key here is that no matter what application you have, TI has solutions for current sensing that will fit into any automotive system. It's clear that there are many ways you can implement discrete high-side current sensing in your system. Both methods shown use automotive qualified devices and can be found in numerous automotive end equipment like displayed here in the infotainment and cluster sector. Each method has its trade-offs, and choosing the right method ultimately depends on your application. All you have to do is match your system requirements to the application at hand, and you'll be on your way. TI's large portfolio of comparators and amplifiers makes it easy to find what you need for any application. If you want to read up more on these devices, please see the appropriate product folder links. If you have any questions, feel free to email me or visit TI's E2E support community. Thank you for watching.